Assalamualaikum and very good day. So this is chapter 1 of our courses, our course SKEE 4433 Powertronics for under School of Electrical Engineering, University Technology Malaysia. So the introduction to power electronics. So what is power electronics? So it is actually a combination of three different fields, okay, that make this power electronic a very complicated field of study, but also very interesting. So it is actually the combination of three fields of engineering, which is electronics. So we are using solid state electronic devices and they are driving circuits, okay, to control the power systems, okay, a very large power system which is controlled by electronics devices, which is such as the diodes, the thyristor, and the transistor. Okay, so in electronics, we have also these components, diode, SCR, and transistor. So to differentiate between the between the semiconductor devices used for electronics and power electronics, so usually we differentiate by putting a name of power at the front of their device. For example, the diode for for power electronics diode is we call power diodes, and then we have power thyristor, and then also we have power transistor. So the difference between this semiconductor in electronic and power electronic is actually on the rating of the voltage and current that this component actually has. Okay. So as a definition is actually power electronic is actually a device to convert and to process and control the flow of electrical power by supplying voltages and currents in a form that optimally suit for the user load. For sometimes maybe the voltage source is 50 volts, but our load requires only 5 volts. So how we want to match the source to the load? So we need a conversion technique where the power is convert or step down from 50 to 5 volt only. But this must be done so in a view of how to achieve a very high efficiency. Okay, so meaning that 100% power from the input is actually transferred to the load without any losses. So that is actually power electronics, convert and in a very high efficient way. So this is some of the block diagram that extract from a journal paper. So as you can see, it's quite complicated. We have the input here, the voltage and current, and then this is the load. So power electronic is used to convert the input that suit with the load. But as you can see here, we have also the feedback control circuit here. So this feedback control can be implemented using any microcontrollers, okay, DSP or FPGA, okay, to give a switching technique, to give a switching signal to the power electronic circuit here. So, but however, for this course, we only concentrate on the introduction of the circuits inside this power electronics system, okay. So this is also another diagram that shows the power electronics. Okay, so typically the power electronic application can be divided under two different application. The first one is the static, where the application involve non-rotating or motions. So usually the system that use this is actually under this category of applications. For example, DC power supply, the uninterruptible power supply, which is UPS, HPDC, heating, cooling, electronic balance, and so on. While for the drive application is mostly related to the to control the motion of the motor, DC motor or the AC motor, and the application can be found in electrical trains, our LRT, electric vehicles, and so on. So this is some industry applications that can be found that use the power electronics. Okay, also the transportations, then also renewable energy. So actually the popularity of the power electronics becomes very high because of the introduction of renewable energy such as the wind and also solar energy. Okay, so fuel cell and also so on. So the introduction of using of this renewable energy has made the power electronics gain popularity much faster than anticipated. So actually in our home appliance, so actually almost of our home appliance have a power electronic application inside. So usually all home appliance that use that all the power supply in our home appliance use power electronics. Okay, our television, our refrigerator, our microwave, and so on. So all that involve power conversion. Okay, we will have a power electronics there. And this is some of the pictures of the power electronic applications. Usually this one is the BIPV, the building integrated PV system. Okay, and then this is diagram on the how power electronic system for the electric vehicles. So this is a vehicle of the Mitsubishi electric vehicle. And this is some of the configuration of the electric vehicles. So we have pure EV, hybrid, and fuel cell vehicle. All are actually use powertrain application here. And this is a wind turbine. And for your information, our country, Malaysia, is not very suitable uh, to use this wind turbine because most of our wind speed is below than the minimum speed requires to to move the what called the blade of the wind turbine here. The minimum speed is 3 meter per second. So our wind speed in Malaysia average is 2.5, I think, meter per second. But at our upper hemisphere, for example, our the German country. So by this year, so they targeted to 100 to their electricity to be fully supplied by this wind turbine. I think they may have succeed it because in 2019 there's almost 90% of their electricity is supplied by the wind turbine. Okay, and this is also another renewable energy, green renewable energy that use polytronics. So we have the wind. So we have here, this is for the to extract the tidal energy. So this one usually the surface is to extract the what you call the wave energy. Okay, this is also wave energy and so on. Okay, so this is some pictures of the home appliance power supply. So actually, as you can see, we have the deck phone, our DVD players, microwave, and inverter. So uh, all have the power electronic system here, circuit here. Okay, okay, this one. So the objective of power electronic is to match the voltage and current requirement of the load to those of the source. So as mentioned before, so this converter power electronic is actually used to convert the source into the output that required to the voltage on current that required by the load. And this conversion can be either in the form of the voltage and current form, which whether it is AC or DC, the magnitude, whether it is and then whether it is single phase or three phase conversion, frequency conversion also, or maybe the shape conversion. And this is the converter classification. So for AC to DC, we call the conversion type as a rectification, and the circuit is rectifier. For DC to AC, it is inversion, and the circuit is called inverter. And for AC to AC, we call cycle conversion, and the circuit is cycle converter. And the lastly is the DC to DC, we call this conversion, or and then the circuit is a DC to DC converter. So, but I want to highlight that for the AC to AC conversion, so it is not very popular because it involves very complicated control on the switching and also the circuit. Okay, usually what we do is we convert AC to DC first and then convert back to AC. And this is the powertrain also involved in the controlling the power flow. So we have unidirectional power flow, so meaning that the source direct is actually the power only uh, supplying the load. Okay, we also have a system that is bidirectional. So sometimes the source is supplying the load, and sometimes also the load is supplying the source, which is the charging and discharging. Okay, so the power electronics can actually control this flow. So that's all. We continue with the second part of the chapter 1. Okay, the second part of chapter 1 is the power devices. So inside this the slide, we will actually introduce you on uh, the characteristic of the devices, okay, such as diode, SCR, and also the transistor. So actually the semiconductor devices usually have this actually have is a classified or categorized under their features such as the switching speed and power handling capabilities. So mostly the device that currently available in the market is somehow maybe they limited for maybe they have the high power rating applications rating, but they are only limited to low switching frequency. Okay, but or there are also some semiconductor that are actually laying here where they have low power capability handling, but can actually switch up in high switching frequency. And there is no devices or semiconductor devices that can uh, that that can uh, that can be found in the market that at this part where you have very high power and high frequency. So no such device has been found yet. Okay, so this is a switching circuit, meaning that we are using the semiconductor as a switch. Okay, for example, the diode here. So the diode will actually forward bias when the anode is positive compared to cathode. So we'll have like this, and when the polarity change, so we will have no output. So this is the switching characteristic. So we have what I call the idle switch and also the practical switch. Okay, so this is very important. So idle switch is maybe referring to when you do simulations. So no power limit, so you can actually can simulate any circuit with high voltage or high current, and there is no zero turn on. And usually the idle switch has a zero turn on, meaning that if you want to if you order them to turn on, so it will immediately turn on and turn off. Okay, and then there is no power dissipations, no losses, and so on. But in practical, they are different because they are produced by semiconductor by a silicon material. So there is some characteristic that you need to actually consider. So the practical switch, yes, they have some limited power handling. So when you are designing a circuit, you need to actually know what is the rating of your power devices. Okay, and then they also have some delayed turning on and turn off. Okay, and then they have some internal resistance. Definitely they have internal resistance, and this will make some losses across the device. So this is the summary of the ideal switch versus the practical switch. And so this is the categories. So we can divide our powertronic semiconductor under three categories. The first one is the uncontrolled, and the component or device that actually under these categories is diode. And for semi-control, we have thyristor, and fully control is all the transistors. For example, the MOSFET, IGBT, GTO, IGCT. So uncontrolled, what is mean by uncontrolled is that we cannot control this diode to turn on and off. It's actually depending on the condition of the circuit. While for the semi-controlled SCR, we can control turn on, but we cannot control the device to turn off. While for the full control, we can both control turn on and turn off. So this is the power diode. So this the figure shows the physical power diode that can be found in the market. So this is the symbol of the diode. Um, okay, so the diode will only turn on when the circuit is forward bias, when the meaning that the anode is positive compared to cathode. So when it is forward bias, it will have some small voltage drop across here between 0.2 to 3 volt depending on the materials used to construct the diode. And when reverse, meaning that cathode is positive and anode is negative, so it is in a blocking state, meaning that it not allow the current to flow. Is it can be modeled as a open circuit, but there is some small current will actually flow, but is a very small leakage current there. But if the voltage across cathode and anode is higher than some value, for example, higher than VR here, so it will make the diode to actually burn out. And burn out meaning that it actually malfunction and it will actually short circuited and the current will flow in the reverse direction. Okay, so in the reverse direction meaning that this diode cannot be used again. And this is the reverse recovery of the diode. Reverse recovery time is actually referring to how fast the diode can actually fully turn off or fully turn off, turn on or turn off. Okay, so this is the TRR. Okay, so it's actually depending on your application. So if you application requires the diode to actually has a very uh, speedy response, so you need to have a diode that has small TRR. So it depends on the materials used actually. So we have the fast recovery rectifiers, which is diode actually, and you have ultra fast recovery diode also, and Schottky diodes and so on. So we have plenty of them. So it's up to you to actually select which one that you prefer the most. Okay, but as you can see here, for fast recovery diode is actually not, for example, here very fast, but the voltage usually is not very high, the voltage rating. Okay, and this is the type of diode that can be found. So we can have the power diode that can be used in the line frequency. Usually diode used in this line frequency has a very low, very large TRR, okay, because very slow response. It didn't actually requires very fast because it is a line frequency system. Okay, and it has a very low on state voltage, meaning that the voltage drop is very low, and the voltage and current rating is also very high. The second type of the diode is a fast recovery diode. So this one have a very what I call very low TRR. And lastly is the Schottky diode. So this diode is very low for drop, and it is used in low voltage, high current application.